Okay, can you see the slides?
Yeah,
The transition is fine as well, right?
it looks like it was transitioning.
Yep, looks fine to me.
Okay, nice. Um, okay. Let me take a look at time. Okay, yeah, it's right time to start. So yeah, so today is our last lecture, and thanks for your efforts throughout this semester. This is not easy class. So before we go to the summary, I want to first to give the schedule of today's class. So first we'll give a brief uh, uh, um, guidance about final review. So some student asked in the Piazza and saying that if we can provide some example papers and show answer case, all kinds of stuffs. I would say don't worry too much about it. This is not calculus 3, calculus 1 or 2. The final exam is really simple, but you do need to spend some time reviewing slides, reviewing homework paper problems. That's it. That web page. If you notice that in the main course web page, there's one line of the date and time highlighted and bolded. Is telling us when the final exam will be scheduled, right? Through the beginning of the semester. So I just want to highlight that if you're not sure, just look at the course web page. If you're still not sure, there's one button, one link beside that highlighted notice, and click into that. There's an official schedule on campus, and just look at because our university has some kind of rules like unique. Our university has some kind of rules like unique rules in scheduling exams. So it's according when those courses are taught every week, and the time interval, and then they just give you, they have already scheduled the time automatically, right? So you just look at that and to ensure everything is good. But here I just want to repeat again. Okay, so it will be on next Monday, May 3rd, from 10:30 to 12:30. So we can now do in-person test exam. So the exam will be on Canvas, will be online. And if you click into this link, you see the bolded notice is the same thing. And so what kind of content will be tested during the final exam, right? So also, so first, you don't need to memorize the formulas. Even you don't need to memorize the concepts, right? Because it's totally open book, open website. And here we have just some rule, right? Do not search questions online. Do not post questions on Stack Overflow and let someone else to answer that for you. But other than that, you can even search for Google. Okay, so it's pretty open. As I want to release the workload for everybody, right? At most, memorizing those things are not is not focus of our course. And the most questions are single or multiple choices. Right? If you have taken any online exam in Canvas, perhaps you see such kind of questions before, right? So then we may ask, okay, uh, uh, which of the classifiers do you think are linear classifiers? We may list a bunch of options like perceptrons, support back machines, deep neural nets, all kind of stuff. You're gonna pick up which one you believe are linear classifiers, right? And it might be single, it might be multiple, but we'll tell you if this is a single choice or it has possible multiple items that are correct. And other than that, there's only one type of questions which need you type something, which is called text description. And because technical constraint, right, we will not ask you to derive some formulas, mathematical formulas. So don't worry. We might ask questions like, do you believe what kind of example question in my mind? So like, what do you believe? Where do the support vectors stay? Right? You can just describe that, right? And or what is the opinion about what is strategic method to extend a general linear classifier to nonlinear classifier, right? Something like that. So it's pretty. So when you write those test description, please hit point. Don't write a lot. That doesn't work. So just try to uh, uh, find a key point and just answer it. Use 1 and 2 sentences. That will be enough. And the last thing might worth your attention, because it's online Canvas exam, we actually have given more problems, um, and every student might be randomly chosen for different set of problems. And most of the problems could overlap, but there are a few problems that may vary. So don't worry, all the difficulties are the same. Okay, any question regarding the exam policy and the possible content?
Yeah, one question. So then the exam is not going to be proctored, meaning like we don't need to be in Zoom and have our cameras on or anything. We're just taking it in Canvas.
Yes, yes.
Okay, sounds
We're
great.
not. I don't. We do not. We don't have like technical
Sure.
devices to watch you, and it's not. I don't think this is really. I mean, the key, right? The key for this exam is not to uh, like select who is doing the problems the best. It's actually is just to enforce you guys to review the lecture slides we have discussed and also the problems we have done, and to reinforce those basic concepts. And problem solve are not like trying to solve some difficult mathematical problem. It's not that stuff.
Right. Okay.
Any other question? Okay, seems everyone is comfortable, right? So what is range, right? What is range of this core of this test? Unfortunately, it will cover the whole semester because we never have had any like midterm exam, right? I don't want students to take exams, honestly, especially for machine learning like classes. The most important thing is that okay, you understand the basic concepts, you know the algorithm steps, you implement it and practice it on real world problems and ensure that works. And that is much more important than any paper scores. So again, this test is just to let everybody to go through what the basic concepts and ideas and the fundamental ideas we have discussed in the class, nothing else. So we're gonna the possible content will cover all what we have discussed throughout the semester. So I will suggest everybody to review the lecture slides. And there is no like extra textbook references you need to take a look at. I don't want to make our workload too heavy, so it's unnecessary at all. But if you have enough time, you're energetic about this, yeah, do it as you wish, right? And also carefully go through the paper problems in the homework assignments, right? So just look at homework assignments. variety of machine learning models and algorithms. And when we look at the details of those learning models and algorithms, we also abstract some learning principles like risk, empirical risk minimization, right? Regularized empirical risk minimization principle, and mistake-driven, and so on, right? And also we introduce some concepts about learning theory, right? We do not go very too deep, go in depth about theorem, but we at least learn some basic concepts, which is called like Pac learnability, such kind of things, right? And then we focus a lot, stress on a lot in the implementation and practice because it's really important. So first, what is learning, right? So here, I want to just read through the concept given by Tom Michel again, right? This is actually in our very first class, right? So learning is to get a capability to generalize to different problems, right? Other than your training problems, right? So usually we say a computer program can learn from some experience E with respect to some class of tasks T and performance measure P. If its performance at the tasks in T measured by P improves with experience E, right? This is very general, but quite formal definition, right? So you can read through this sentence several times and to get meaning and connect them to the detailed algorithm models I learned so far, right? Actually, every model and algorithm learned actually is practicing this concept. Right? And then when we conduct some particular machine learning tasks, right? We need to give some like learning protocol. We need to define some necessary gradients, right? So throughout the semester we focus on the supervised learning, right? Although in addition to supervised learning, you have unsupervised learning, you have semi-supervised learning, but no doubt supervised learning is the most important. So when you do unsupervised learning or semi-supervised learning, you will see that it's just a normal extension of supervised learning, right? So of course we need to know what is the basic concept of supervised learning, right? So to conduct a supervised learning, we must be clear what is our instance space, what is our label space, right? So instance space consists of all possible examples that need to be classified or predicted, right? And then label space are the set of possible labels, right? For example, if you're doing binary classification, then your label space just consists of two labels, right? Say if you do the email spam detection, then your label space consists spam or not spam, or positive, negative examples, and so on, right? If your label space are continuous, right, mean that labels could be continuous values, then you're doing regression, right? So actually, the label space determines the type of the supervised learning tasks, right? And our underlying assumption about supervised learning is that there is some ground truth function which can give the correct label of every instance in the instance space, right? So call this ground truth function as target function. And the goal of the learning is to find out this target function, or at least to find some approximation to the target function, right? To do that, we need to specify a hypothesis space, right? So, and then in the supervised learning protocol, we use a set of training data to guide our search over the hypothesis space so that we can identify the function that is closest to the target function, right? So the hypothesis or the function, right? So if your hypothesis space is large enough, right, which contains the target function, you might be able to find the real target function, right? Otherwise, you might never be able to find out the target function. You might only be able to find the closest one, right? So that also relates to the agnostic learning setting, right? Remember that the agnostic learning saying that, okay, my target function might be outside my hypothesis space, meaning that we can, if you just search inside your hypothesis space, you'll never be able to, there is always some gap between the target function and the hypothesis. Right? And of course, when we change the setting of the training data, we can have other learning protocols. Like if you don't have labels for the training inputs, then your learning becomes unsupervised learning. If you have partial labeled examples and partial unlabeled examples, your learning becomes unsupervised, semi-supervised learning, right? Which we did not discuss in this semester due to the time limit. Right? But you should know what's the definition of supervised learning, unsupervised learning, and semi-supervised learning. What do they mean differ from each other? So in a supervised learning framework, we have discussed a variety of learning models, like decision trees from the very beginning, right? And then we talk about how do we combine multiple weak models together, which ends up with boosting ensemble methods, right? The typical example include AdaBoost and Random Forest, which use decision tree as the base learners, right? And then we talk about least mean square method for linear regression, perceptron, right? Perceptron is a linear models and support vector machines, and then kernel tricks, right? How can we generalize linear models or linear classifiers to nonlinear models, nonlinear classifiers? This is a very powerful trick, right? And also to the generalization of the support vector machines must be done in a dual domain, right? In the dual form, and then we apply the kernel trick. And we also let's now discuss this actual bonus question, right? How do you extend perceptron to the kernel versions called kernel perceptron, right? And kernel SVM. And then we talk about how to build up a nonlinear classifiers or nonlinear regressor from scratch. Now, rather than using some nonlinear feature mapping tricks, right? It's called artificial neural networks. They are the most popular and maybe the hottest research area in machine learning right now, right? And also the K training algorithm is called backpropagation, which is essentially an application of the chain rule, right? A smart application of chain rule. And finally, we introduce the notion of probabilistic learning. We give a prominent example, it's called logistic regression, right? So according to the learning principles and types of models, we can categorize our machine learning models in different types, right? So first, we can the easiest way will be we can simply classify or categorize our machine learning models into two types. One is linear models, one is nonlinear models, right? So linear models are include like least mean square methods for regression, perceptron, the original support vector machines, and logistic regression, right? And then another type of methods called nonlinear models, right? So typical methods are based on kernel tricks, right? Like kernel perceptron and kernel SVM, and also neural networks, which are constructed. The nonlinearity is constructed from the scratch, right? And then decision trees, right? This one, you should be clear, right? Decision trees, although they look simple, but they're not linear models. They're nonlinear models, right? And AdaBoost and Random Forest. And from another aspect, we can categorize machine learning models into probabilistic models and non-probabilistic models, right? So although we just briefly introduced the principle of probabilistic models, but actually probabilistic methods are very big branch in machine learning, right? So we only talk about logistic regression, right? And then we spend most of time in this semester in non-probabilistic models, neural networks, decision trees, support vector machines, perceptron. But I can tell you, all those non-probabilistic models, they can be converted into probabilistic models. So they all have probabilistic versions, like decision trees, they can be converted to Bayesian decision trees, or Bayesian neural networks, or Bayesian support vector machines, and so on. And when we throughout our discussion about those machine learning models and algorithms, we also introduce some basic concepts and ideas in computational learning theory, right? So the most important concept is called Pac Learning, right? Probably approximate correctness. So everybody should know what is the definition of Pac learnability. That does not mean like you need to recite the definition of Pac learnability. I know it's very tedious, it's very long, right? You need to, there are four, there are about like 4 conditions and blah, 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 right? But you need to know the definition. When you read out the definition, you should know the meaning, and also you should know why they're defined like that, right? So for example, Pac learnability is not some deterministic learnability, meaning that in computational learning theory, we can never guarantee an algorithm in whatever cases can give you like 95% prediction accuracy. Why? Any thought?
Because its accuracy also depends on what training data it's given.
Yes, exactly right. This is a very, very important insight. Right? We're not asking, we will not ask you to recite the definition of Pac learnability, but we might ask some question like that. Right? Why not? I just state a machine learning algorithm that give you absolute accuracy 5% error, like in error cases. Do you think it's possible, right? So you should hit that point, right? So because the learning, no matter how powerful your learning algorithm is, right, it also limited to the quality of the training data, and the training data itself is random, right? It is collected from some unknown data distribution, right? So sometimes you get good training data, you get good performance. Sometimes it's not, it's bad, right? So that's why we can always say, okay, with high probability, the learned hypothesis get the generalization error less than something, right? So it's a probability statement rather than deterministic statement, right? And then we talk about the sample complexity bound, right? So to achieve some probability statement of performance, what's the lower bound of number of training examples, right? And also we talk about the generalization error bound, right? So again, there won't be any question asking you to derive some specific error bound or sample complexity bound, but at least when you are presented such a bound, you need to know the meaning, right? Like we know from the agnostic learning, right? General agnostic learning, we derive the generalization error bound. We know that the generalization error is determined by 2 terms, right? One is training error, the other is the term that is related to VC dimension, right? You need to know, you need to explain how VC dimension will affect the bound and also the risk, right? And how the training error will affect that, right? And also VC dimension, what's the definition of VC dimension, right? And why do we introduce VC dimension, right? Because in the because the hypothesis space is infinite, right? That when a hypothesis is finite, and we can derive something just based upon the size of hypothesis space itself, right? But what if the hypothesis space is infinite, right? And you cannot just use log size hypothesis space, it's infinity, right? We need to use other measurement to compare different infinite hypothesis spaces because they have different expressiveness, right? Look at our examples, right? When we introduced several different types of infinite hypothesis spaces, their expressiveness do differ from each other, right? And also, what is the logic of deriving the large margin principle, right? So when we introduce the fallback machines, this might be the most elegant machine learning model, which is purely invented based on the theory, right? And it all comes from this generalization error bound, right? How does generalization error bound relates to data dependent VC dimension? How does data dependent VC dimension relates to the large margin principle, right? You should know the whole logic chain, right? Of course, you're not required to memorize all this, right? But you need to know how the support back machines, this large margin principle is motivated, right? Is invented, right? And this where does this insight come from, right? And learning principles, right? So we spend most of our time in talking about the empirical risk minimization principle, right? So the examples include least mean square method, perceptron artificial neural nets, right? So, but what is the empirical risk minimization, right? So this is just gives us a general way to conduct a learning model to conduct learning procedure. So what you need to do is that, okay, you specify the model, and then you define a loss function on the training data, right? And you calculate the loss over all the training examples, then you update the model. You actually essentially to minimize the training loss. This is called empirical risk minimization, right? But there's a problem for the empirical risk minimization. What is that problem? Overfitting, right? So if your data has some kind of noises and then you overfit data, that noises can hurt your generalization performance, which we have already discussed in talking about decision trees, right? Even your data has less noise or has little noise, right? And empirical risk minimization still is problematic. Why? Because it will mislead you to select those complex positive spaces, right? You tend to use highly complex models like artificial neural nets to fit the training data because it is easier to get better, smaller training loss, right? But then it violates the Occam's razor's principle, right? So what is Occam's razor's principle? Any thought?
Isn't it essentially to pick the simplest? If there are many models, if there are many options to choose from, pick the simplest option.
Yes.
That give the same result.
Yes. So actually, in practice, you'll find that it's not always like that. The more complex the model you have, the better it is. So actually, you always need to find a trade-off between the model complexity and data fitness, right? That's why we introduce so-called regularized empirical risk minimization, right? So in addition to the training loss, we add some regularization term to penalize those over-complex models, right? So the typical example is support back machines, right? We have that half W transpose W term, which reflects the large margin principle, which is essentially to penalize over large VC dimensions, right? And also map estimation for logistic regression, right? Map estimation is to trying to maximize the posterior probability, meaning that you're accounting for both the prior and the likelihood. Right? Likelihood reflects how you fit data well, right? But prior actually restricts the complexity of the model, right? And then those are about the remaining are about the probabilistic learning, right? What is maximum likelihood estimation? What is map estimation? And what is the connection between MLE and MAP, right? Some student has pointed out during our discussion, right? You can view MLE as a special case of MAP if you view the prior simply uniform constant prior, right? And the learning algorithms, right? So from the perspective of learning algorithm, we actually focused on the most popular learning strategies in machine learning, which is based on gradient descent, right? And gradient descent is stochastic gradient descent, right? So what are their differences, right? What are advantages and disadvantages, right? So everybody should be aware of that. Gradient descent can always give you accurate gradient, right? Meaning that if you can apply gradient descent, you don't need too many steps to arrive at some local minimum or global minimum, whatever, right? But the cost to get one accurate gradient is quite high, especially for large data, because you need to go through every training example and to calculate the full gradient, right? But on the contrary, our stochastic gradient descent is much cheaper to compute one update. Why? Every time I just sample or just randomly use one example to calculate gradient, I use that to approximate the gradient and perform the gradient descent. Right? So this update is much more frequent and much easier, but each update is much less accurate than the true gradient descent. Right? So everybody should know their differences, right? The advantage of gradient descent is that it's more accurate, right, but more costly in updating, right? The stochastic gradient descent, the advantage is that it can be updated much more frequently, so it's much more favored in large data, right? Disadvantage is that, okay, you might spend a lot more updates to converge than gradient descent, right? So Then from practical perspective, right? We know that nearly all the machine learning algorithms, you need to specify some hyperparameters, right? And then how do we generally select hyperparameters? How do we generally identify the optimal hyperparameters, right? So I have introduced several strategies like cross-validation, right? Or you can use one holdout data set and use the performance at holdout data set to approximate as a proxy to the generalization capability, right? And then you just tune that on the holdout data set. Right? So those are like brief review of what we have discussed, right? We do not go into very much details. Here we just give some like view in what we have discussed, right? And hopefully when you go through those slides and all those paper problems, you can think about and organize what you have discussed, organize your knowledge in those different viewpoints. Then you will feel much more confident and feel much more comfortable, right, when you take the final exam, right? So again, the suggestion for the review is very simple. You don't need to practice any paper problems. Just carefully go through all the lecture slides, understand the details, like those stuffs, and go through all the homework problems you have worked. Right? So I believe our TMs have released the homework, the answers, the answer keys for the homework paper problems. So you can use them as a reference, right? And again, you do not need to go through the programming problems. Good luck to your final exam. So any question regarding the final exam again? So is everyone comfortable? Okay, great. So let us, we're gonna use the remaining, sorry. Can you see the slides?
Mm-hmm.
Yeah, so we're gonna use the remaining time to give some practical advice for building machine learning applications, for real world machine learning applications. You'll see that when you apply machine learning in real world problems, it's not that machine learning only, right? You need to take care of other components and things altogether. Right? So hopefully that will benefit you in the future if you really want to apply machine learning someday in some practical problems, right? So the outline for this part of topic consists of 3 parts. Right? First, we're going to talk about what's the general strategies to diagnose your learning algorithm, and how do we conduct analysis, and finally, how do we inject machine learning into your favorite task. Okay. So first, how to diagnose your learning algorithm, right? So namely, how to debug, right? So here, I mean, the debug does not mean you have some bug in your code or some problem in your code, which you have already done a lot in our homework assignments, right? So you're given some data, you know the list of algorithm steps for fallback machines or artificial neural nets, where you need to just code those algorithm steps and test on data, make it work normally. I'm not saying this. I'm saying that how do you improve your existing learning models, given that your learning models are correctly implemented, right? Suppose you train an SVM or some logistic regression or artificial intelligence, right? For some task like spam detection, you have collected a bunch of practical data, right? So you obviously follow the best practices for finding hyperparameters such as cross-validation holdout data set, but your classifier is only 75% accuracy. Then what can you do to improve it? Right? we do not assume that you have your implementation has some is problematic, right? So how can you do it? How can you improve it? Right? Any thought?
Maybe applying a kernel trick to it to make it more rich.
Yeah, that's a good strategy. Any other suggestions?
Possible maybe do some further like feature engineering to try and extract more features from the data.
Yeah, excellent. Right. So actually, the strategy you mentioned that can be categorized into several types, right? So first, we forgot to mention, right? We can collect more training data. This is the most straightforward way, right? So perhaps your low accuracy just because your number of training examples is too small, right? If we add more, we expect that we can improve a lot, right? And then feature engineering, right, as Michael said, right? So we can consider adding more features, more discriminative features, more indicative features, right, to help us better classify spam or non-spam emails, or we can delay some useless features, right? And those useless features might hurt the learning procedure, right? Or we can discover or even construct other features, right? In addition to that, right, we might come up with some other training procedure, right? Like we can focus on the same training model, right? But we want for more iterations, right? Or we can use a different algorithm. Like Spencer said, okay, we can use kernel trick, right? Or we can switch to other model. Like it's not necessary to be support vector machines. It can be artificial neural nets. It can be random forest, right? It can be AWS, right? Use different algorithms, use different classifier, or play with regularization. Like for example, if I feel like, okay, I'm just doing maximum likelihood estimation, I think it's not enough. I should do a regularized empirical risk minimization, meaning that I should do some map estimation. Right? But we know that, okay, there are many kind of ways to go, right? So trying enumerating all kinds of ways are tedious, right? And prone to errors and depends a lot, right? So what we need to do in practice is to make this process to improve your model to be more systematic, to be more methodological. So first, given the current performance, right, which is not ideal, we need to diagnose where the problem is. We need to ensure we know the problem, and then we can take the action to address that, rather than randomly pick up, try this strategy, and then randomly try that strategy, and randomly combine them together and see if it works, right? Then that you don't have an explicit direction. It's very inefficient, right? So how can we diagnose, right? We need to know what is the set of possible problems. So we know the common problems for not ideal performance are overfitting, right? You overfit the training data too much, right? Maybe you use complex models, the model has a high variances, so it leads to overfitting, right? Or underfitting. Your model is too simple. For example, this problem is highly complicated, but you just use a linear regression. That might be not sufficient. And third one is that, okay, your learning is not sufficient, meaning that your learning does not converge. The optimization procedure is far from converge. And finally, perhaps your measurement is problematic. Right? You're not taking the right measurement. Right? There are possible other reasons, but here we just summarize the four most common problems in your machine learning models. You need to first to identify which problem causes the unsatisfactory performance, and then it will be easier to fix the problem if you know where it is. So So first, how can we detect overfitting and underfitting? So overfitting means that, okay, your training accuracy is much higher than the test accuracy. So it says that, okay, the model explains the training data set well, but poor in generalization. So then you can take a look, right? You can take a look, okay, what about training accuracy? What about test accuracy? And underfitting is another way of saying that, okay, the accuracies on both training test sets are unacceptably low. Right? That means the model cannot well enough represent the target concept, or well close enough to the target concept. So to differentiate underfitting and overfitting things, we can try to investigate the learning curves. So we can try to draw a curve where the x-axis is the size of training data, and y-axis is just the error. Right? So we can first look at when we increase the size of training data, how does the training error vary? Right? So of course, if the size of training data is very small, right, it's very easy for your model to fit that training data to get low training error, right? But when your training data gets larger and larger, of course, it is not that easy to get zero training error all the time, right? And then you can take a look at when you're given a relatively large size of test data, how does the test error vary along with the increase of training data? Which we usually refer to as generalization error. If there is a significant gap or large gap between the training and test error, right? What does it imply? If the gap between the training and test errors are large, what does it imply?
Overfitting?
Typical overfitting problem, right? So you get very good at the training, at inflating the training data, but the test performance are not good. Right? So it's typical overfitting, and overfitting typically happens on complex models like artificial neural nets, right? So, and then in that cases, the typical behaviors will be like this. Right? When we increase more and more training data, you see the gap between the test error and training error is kind of reducing, right? In this case, you're saying one effective strategy is to add more and more data. So from this curve, right, from these two curves, how the training error and test error vary along with the increase of training data, we can say, okay, this is a typical overfitting issue, right? Meaning that your model is quite complex. In that case, okay, if you have enough resources, you can try to add more training data, like artificial neural nets. Right? So more than artificial neural nets, especially for large neural nets, you have to feed them with like millions of training data points. Otherwise, they won't give you good generalization performance. But what if this, right? We see that the generalization error and the training error are quite close to each other. And they all kind of converge to a high error level. What does it reflect?
Underfitting?
Yeah, it's underfitting. Why? Because the model is quite simple, right? The model is quite simple means that it does not overfit the training data, right? And its performance when the training data changes, the model does not change too much, right? So the performance on both training data and test data are kind of close. Right? In that case, like adding more training data is not that effective. Why? Because your model capacity is there, right? You add more, adding even more training data does won't help it to get even better performance. Right? And then in that case, you might need to switch to more complex models. So now we can see like by just joining the learning curves, right? Look at the training error and the test error along with the size of training data, we can detect if this is just learning with high variances, namely complex models, or learning with high bias, meaning oversimplified models, right? And then we can take actions corresponding actions. And now let us get back to how to improve our model, right? So as we just discussed, right, we have listed a bunch of strategies, possible strategies which can help improve our model, right? But we need to know which each strategy, in which direction they're gonna help with our model, right? Say, if you can provide more training data, it usually helps with overfitting, but it does not help with underfitting. Why? Because your model is too complex, right? Adding more training data won't help. If you use more features, it really helps with underfitting. Why? Because it's actually increase the hypothesis space of your model, right? Like if you have linear models, right? If you have linear models, if you only have like 5 features, now I extend it to like 100 features. Of course, your hypothesis space is enlarged, right? And hopefully you can increase the expressiveness of your hypothesis space. Right? If you use fewer features, it really helps with overfitting. Why? Because it reduces the complexity of your hypothesis space, right? And if you use other features, then it's hard to tell. It could help with overfitting or underfitting or both. And play with regularization. This is really to help with overfitting because it's penalized overcomplicated hypothesis spaces, right? Okay, any questions so far? Okay, so everyone is comfortable, right? So we now have discussed about how to detect the overfitting, how to diagnose overfitting issue or underfitting issue, right? So now let us look at another two common seen problems, right? The first, what if your learning does not converge, right? The learning behavior is problematic, meaning that okay, it is too early to say the performance, to check the performance, right? So how do we detect the learning, the convergence of learning? It's very simple, just to draw how you're learning, how the objective function of your learning problems vary along with number of iterations. You might have done that in our homeworks, right? So we can just look at how many updates, like stochastic gradient descent updates or gradient descent updates or iterations, right? And how the objective function varies, right? So if you stop at here, obviously, it's not converged, right? It does not converge, and the performance if you take the parameters, model parameters here, and then you test the performance, those performances are not is not reliable. You should look at the place where the model the learning has truly converged, right? Like here. But sometimes just looking at the learning curve is not always easy to decide. Like if you look at here, right, you can see that okay, looks like the objective is still trying to decrease, but it's not. It does not decrease that much. And should we choose to stop here? Right? Our suggestion will be like you should run long enough. Right? If you see the truly convergence, and then you can determine a point which is early before the true convergence and to stop. Right? This is like early stopping technique we have discussed before, right? You can use some held out data set and say if the performance on the held out data set doesn't no longer improve, and then you can stop. But what if your learning objective functions varies like this. If your objective, if your trajectory of learning objective is like this, there must be something wrong in your code. Right? This is really really relates to your implementation. Right? It might be because, okay, say if you're using some stochastic optimization techniques, it's at early stage. We know that if you apply SGD, right, your curve, your objective function is kind of like perturbating at the beginning, right? Especially if large step size, right? The fluctuates quite much at the beginning, right? But you should always see a trend that roughly that finally kind of like going down and then tends to converge. But of course, the stochastic gradient descent should be like that, right? It's kind of a small perturbation, but it's still you can see the general trends, right? If your whole learning trajectory is like this, right? It's highly unlikely that your learning algorithm is doing it normally. Right? There must be something wrong. Right? You should look back at your code. And if we're doing gradient descent on convex function, an objective count increase, right? That is talking about a gradient descent framework, right? Meaning that every time when you do the gradient descent, right, you always decrease the function. That won't be any there won't be any perturbation. What you can see is just always a function decrease, the trend of the function decreasing. Okay, any question? Okay, so when we try to use different ways to improve our model, like say we use different algorithms, like to ensure you use your algorithm is appropriately applied, right? Try to track the objective from convergence, right? Otherwise, the accuracy, all kinds of stuff may not be reliable enough. So and finally, we need to diagnose, right? Are we marrying the right thing? Right? This seems kind of like weird, right? But in practice, things are always like that. Things are always happen. For example, if your data set is unbalanced, we know that in our problems, in our homework problems, right? The most common used metric is just the prediction accuracy, right? If you have 100, 500 examples, 500 test examples, you look at how many labels you correctly predict, right? And it just divided by 500, you get accuracy, right? If it is 99%, well, we can celebrate, right? But in practice, it is often the case that your data set is highly unbalanced. If you simply use the accuracy, and that measurement will be very misleading, right? For example, if you diagnose some cancer, right? You know, like people, the ratio of the people who have cancer is very small, right? Like normally just 10% or 0.1 or 0.001%, right? Like for example, maybe for every 1,001 examples, 1,000 are positive, only 1 are negative, right? And then I can create a naive classifier, right? I always predict the examples are positive. Then, no matter in what kind of cases, we get 99.9% accuracy, right? But is that classifier meaningful? It's not meaningful at all, right? So for those unbalanced classification tasks, simply use the accuracy, prediction accuracy is not valid. It's not is very misleading because you can simply predict the majority label, right? And you can always get very high accuracy. So it's not meaningful at all. That's why you may see our Kaggle computation tasks. We're not using prediction accuracy to measure your performance. They actually use a measurement is called area on the ROC curve, right? So of course, I mean, due to the time limit, we're not able to explain in detail what does it mean, right? But basically, it actually get rid of those special cases where you can use a stupid classifier, give you a very high accuracy. Right? So for those unbalanced labels, what are commonly used measure, right, to compare the performance of different classifiers and models, right? So the commonly used include precision, recall, and F measure. Right? F measure is actually a harmonic average of the precision recall. And of course, you are not required to get to the detail what's that mean, but you should have some impression that, okay, prediction accuracy is not always a good measurement. Right? And also another common is just AUC value. Okay, so we now have finished the discussion about how to diagnose our learning algorithms. So any questions so far? Is everyone good? Or you're not interested in doing in this? How to apply machine learning practice in practical applications?
I guess it makes sense when you say it. It's just when we, I guess, apply it, it may not make much sense then. But as you're talking about it, it makes a lot of sense.
Okay, yeah. So let me know if you have any questions, because I do believe this is those practical suggestions are much more important than just the final exam. Right? So don't worry too much about the final exam. Do your homework, and if you're doing great in your homework and project, you'll be very good. You'll be very good in the final exam, right? You'll be very good in the final grade. Right? So don't worry too much about final exam. Just spend 2 or 3 days review all the lecture slides. So the next things I want to talk about is about how to do the error analysis, especially when you put your machine learning model algorithm in a system, rather than you just treat machine learning as a whole word, right? So in our class, machine learning is the whole, right? Is a whole thing, right? What you need to do is to look at this ML code and try to debug it and try to make it work, right? But in practice, is machine learning is just a small, tiny, maybe it's a K component, maybe it's not a K component, a much larger system. Right? For example, this is just a typical system components, right? When we embed some machine learning, right? This system can be some online advertising system, can be online tax mining system, can be whatever, can be online weather forecasting system. Right? You have some configuration, and they have a configuration model which can interact with professional users, right? And you have some data collection component which you can continuously retrieve data and pre-processing it and store them in the database. You have a feature extraction component which might interact with several feature engineers. Right? And you have data verification because you need to ensure that your data is clean, your data is correct, your data does not contain any adversarial content, right? And then once you have got all those data and the things are ready, you can feed them to your ML code. So ML code is take a tiny portion of that. And then based upon your ML code's output, there are some analysis tools, right? You can say, according to our ML tools, what kind of output I'm giving. Like, it's not always like ML code give the final prediction. Like ML code usually won't like in advertising, it won't just tells you which particular advertisement will be selected to show in front of your the browsers. It's not like that. It usually will be fed into an actual layer, like and combining with some expertise and heuristics, and then to determine the final advertisement layout and advertisement the selection of bidding things. And in addition to that, you also, because those components are usually deployed on the distributed system, right? You have to have some machine resource management, right? So when your resources are limited, how do you reduce the throughput of the data collection or other work amount? Or when you have enough resources, how do you automatically expand more cluster nodes, right? And also you have some process management tools which allow the administrators to monitor system. You also have put everything in the service infrastructure is based on whatever computer clusters, right? It's in Google or Amazon AWS or in whatever, right? So you can see it's pretty complicated, and it's very hard to just extract this specific component outside and use our telescope to study it. It's very hard, right? And then how do we conduct error analysis? Right? So here are a few principles, right? So first, generally, machine learning plays a very small role in a larger application. So before we conduct any machine learning, we need to consider pre-processing step, and then feature extraction step. And the feature extraction might also be based on other machine learning-based methods, and then we need to perform some necessary data transformations. And then we can feed to machine learning and give and then the machine learning's output the predictions are fed into the next steps and then give to the end users. Right? So, and we need to know how much do each of those contribute to the error. Right? And only when we know this, we can explain why the system is not performing perfectly. Right? Otherwise, we cannot find what is the problem. Right? So here I will discuss about it with typical text processing pipeline, right? So suppose you have an NLP, a natural language processing system, right? And text mining system, right? So the data source comes from text, right? Extracted from corpus or from online corpus, online text resources, right? And the text will be first split into words, and then we run some parts of speech tagging component, which is usually based on machine learning as well, right? And gives the parts of speech tagging, and then those words and parts of speech and also text sequence itself will be fed into the next component to do the parsing, right? So the parsing to generate a bunch of synthetic trees, right? Those are syntactic trees, and those syntactic trees actually represent the semantic meanings of those sentences in the text. Right? And finally, the features or the structures from the parts, the syntactic trees, part of speech taggings, and even word itself are synergized together and fit into some machine learning-based application. For example, sentimental analysis, or news recommendation, or text automatic summary, whatever. Right? So we can see that although this seems our killer application, right, which is based on machine learning, but each pre-processing component can also be machine learning driven, right, or some deterministic based or rule based, right? But still, it has some errors. Then how do we examine like which part of those components, which component contributes how much error in giving the end performance? So a commonly used trick is to do a one-by-one test. That is, we plug in the ground truth for the intermediate components and see how much accuracy of the final system changes. And you'll see which component actually takes the biggest responsibility, right? So for example, if I have a system here, right, I know that my end-to-end prediction accuracy is only 55% accuracy. Right? And now I'm gonna replace each component by some ground truth and see how much accuracy is improved. Right? Say if I replace the words processing component just by the ground truth set of words, right? I found out, okay, the end-to-end prediction accuracy is now increased to 60%. Right? So improved the 5% accuracy. It sounds not that big, right? And then I further replace the parts of speech tagging component by some ground truth parts of speech, right? Say tagged by human beings, right? And then I found out, okay, now accuracy increases down to 84% accuracy. It's a giant improvement, right? And next, we replace the tree parsing component by ground truth parsing trees. Again, this might be done by human beings, right? And then we further improve the accuracy to 89% accuracy. And finally, we replace the ML-based application by human beings. Well, by any ground truth, you might get 100% accuracy. And then by looking at the varied accuracy after replacing each component by some ground truth, right, we can clearly see the error in the parts of speech component hurts the most. Why? Why?
Because the accuracy changes the most in that.
Yes, exactly right. We found out, okay, if we just replace it by the ground truth, by the oracle, right, the accuracy increases a lot. Right? That means, okay, the original component is very bad, right? It's very bad and it's far from satisfactory and influence the system, the overall system's performance the most, right? And what should we do in the next step? We should try our best to improve this part of speech tagging component, right? Perhaps we need to replace this part of speech tagging with the state of art, right? Say based on neural networks, transformer architectures, and we should train better parts of speech tagger, right? With larger corpus, whatever. And then we can redo this error tracking again and see which component is the bottleneck, right? And then we can improve it, and then we do this iteratively until our overall performance is satisfactory. Any questions so far? Okay, so it sounds pretty intuitive, right? But this is a very commonly used engineering practice when you do the real world application, especially when you are in the industry, right? You always need to debug a much more complex system than you think, right? We need to take wise steps rather than just randomly probe. Right? That won't give you a systematic improvement, and that would make people like more and more panic. And then another common used approach is called ablation study. Right? So usually it's seen with speech engineering. So suppose we have a collection of features and our system does well, right? But we don't know which features are giving us performance. And how can we do the ablation study, right? Again, we can view the whole set of features as a whole, whole set of features as a holistic set, right? And then you're just trying to use fewer features, meaning that you delete those features one by one and say which deletion of features will cause a large change of the system performance. Then you get to know which feature or which set of features are important, right? And if that order takes in matters, you can random order these features in different times and do this again and again. Then you can summarize all the results, and then you know, okay, which set of features are important, and then you can investigate why those features are important. So here is the principle, right? So doing such kind of error analysis is very important because in practice, it is not enough to have a classifier that works. It is usually much more useful and valuable to know why it works. Because it not only helps us to interpret predictions and diagnose errors, it can also provide audit trail, right? And also we can expect to add in this how much performance we can get, right? And when everything becomes like as expected, right? We can predict what will happen in the future, and then things becomes much easier. And then the last thing I want to discuss is about how to implement machine learning or inject machine learning into your favorite task. Right? So again, this is all about the practice, right? So it's different from what we did in the machine learning class, right? So for example, if your boss gives you a task to develop a classifier to classify fishes, right? Suppose you want to build a classifier to identify whether a real physical fish is salmon, tuna, right? How do you go about this? We have two types of approach. One approach is called slow approach. Typically, we'll carefully identify features, get the best data, the software architectures, and maybe we need to design some new learning algorithm rather than use off-the-shelf algorithm, right? And then we implement it and hope it works. So the advantage of doing this is obviously this is a kind of a very serious study, right? So you have a higher chance to get a better approach, and maybe even a brand new learning algorithm is more like research oriented, right? So now I want to ask, what is the disadvantage of this approach?
It could take a lot of work and a long time to build and develop a good model.
Yes, exactly, right? You hit the point. This is actually not favored in practice and the industry at all. Like if your boss gives you such a task and you spend 3 months in looking at features and design the softwares and then derive mathematical details and then get some initial results at 4 months. After 4 months, you're very likely to get fired. So this is always not encouraged in practice. Right? So in practice, you're always encouraged to use the so-called hacker's approach. What is hacker approach? Implement something as quickly as you can. Right? You can choose to start with like just linear classifier, support vector machines, whatever you feel comfortable, confident, reasonable. And then you can get some initial results. You can report to your boss, right? And then you can use all kinds of diagnostics and error analysis tricks we have discussed to iteratively improve your classifier. And then, I mean, from your boss perspective, right? He will say, okay, you are making progress every day. Right? You are making your classifier better and better, and finally it reaches to some satisfaction level. Okay, you're done. This job is perfect. So he will figure that. And otherwise, right, if you use slow approach, right, you spend like 4 months and still take risks to end up with a bad result. Nobody or no company or no organization will figure like that, except like academic. Right? So in practice, please always use the hacker's approach, right? Because it gives a faster release. Right? At least give you some solution. Maybe the solution is not ideal, but at least it's some solution. It is some solution. It might be useful shortly, but you have a lot of room to improve it.
And my impression has been that basically if you're not quite sure what that first implementation should be, you should probably just pick neural nets. Sounds like they're pretty much gonna be like, it just seems like it seems like that's probably a good place to start in general, unless you already know right off the bat that you're the problem is well set up for some other algorithm.
Yeah, neural network is definitely one choice. Or even you don't need to, if you're familiar with neural networks, yeah, go ahead and use them. Right? Even you're not familiar with it, you can use whatever linear classifiers, nonlinear classifier you feel comfortable with.
Okay, it just seems like to me like that neural nets are probably the most popular choice in general. Hard to say.
It's hard to say. It's really
okay.
The problem itself.
Sure.
Like,
okay.
Like your problem is related to image classification or image processing. Yeah, neural network is the first choice. But problem is not that hard. Like it's not massive data, right? And
well, that's true. Okay.
You only have 100 examples. So, I think the first choice will be SVM.
Okay. Okay. Good to know.
Yeah. But anyway, in practice, you should use the hackers approach, right? And based on whatever you're familiar and comfortable, and if you do feel it is reasonable, right? You pick up some algorithms, some models to test, and to give some to deliver something, right? And then based upon that, you can diagnose what is the problem and then in which direction we can make it better. And finally, when you have a delivery model, you have to implement a model, right? And you need to show that to your boss or to your colleagues that works, right? And then you need to make sure that you have the right evaluation metric. So the commonly used metric, we have done that before, right? Like using mean square error, like absolute error, or classification accuracy, or AUC, whatever, right? But in addition to that, in many practical applications, you might have to come up with your own metric. In that case, you need to convince your colleagues or your boss those metrics proposed by you are unbiased or at least reasonable. Right? But that really depends on applications. Like for example, in online applications, in online advertising, right? How do you evaluate your prediction about the clicks model, right? Is correct or not? Is good or not? Right? And once you have a right evaluation metric, you also need to think about whether your loss function have reflected those evaluation metric. Right? And a final thing, right? The final thing which you should be aware of is never try to mix your training and test set, right? Because the learning is always the generalization to the new examples. So whenever you see your model is incredibly working well, don't hurry to celebrate, right? Look at if you have accidentally put your test data into the training set, because this kind of like very low level errors, but it's very common in machine learning practice. And in addition to that, other principles including like be aware of bias and variance trade-off, namely overfitting and underfitting. You don't want like too complicated models which are only overfitting. You don't want too simple models which can be underfitting, which cannot give you a good performance, right? You always need to find a good trade-off. It's between the two. It's not like toward an extreme. And be aware that intuitions may not work in high dimensions, right? And unfortunately, in machine learning practice, you always need to deal with high dimensional data. So there's no proof on picture and has some curves of dimensionality. So the often used trick will be like, I'm gonna project the high dimensional input in the low dimensional space and to get some like intuition. But again, that intuition is not guaranteed. And finally, don't believe too much in theory, because theoretical guarantee may only be theoretical. There are many beautiful theories in machine learning, but if you take a close look at those lemmas and the corollaries, you see that they're under very strong assumptions, and your practical problems may be very different from those assumptions. So you might not realize that your problems have already violated those assumptions. So if it's not expected as what the theory predicts, that's fine. That's totally fine. And big data is not enough, but more data is always better, right? And also data cleaning is even better, right? So that is called data processing, right? In this class, because we have already processed the data of everyone, so you don't need to worry about that. But in practice, there are many tricks and engineering work about data cleaning, data cleaning pipelines. All those are of critical importance to your final prediction accuracy. So learning requires knowledge to guide a learner, right? So machine learning is not a magic wand. It's not like, okay, everything you can apply machine learning and it gives you a good performance. It's not like that, right? So, when you have more and more knowledge and experience, you'll get to know which type of models is right for some particular type of task, right? For which types of tasks, you know, okay, linear models are good or decent enough, decision trees are decent, or deep neural nets are good, right? Well, at least for my experience, right? For my I have in this area for decades, right? Not for decades, for 1 decade and more. I know that deep neural nets work for some areas, but do not work for some other problems, right? I know decision trees are good enough for many mathematical applications, right? And linear models are good enough for, say, for advertisement prediction, all kind of stuff, right? So the more experience you gain, the more kind of sense of prior knowledge you will accumulate, right? And also you will know which learning algorithm, right, is appropriate, and then you will know whether the data will violate any crucial assumptions that were used to develop or deploy the learning algorithm. And feature engineering is crucial, right? Which we have emphasized a lot, right? And finally, it's some like miscellaneous advice, right? Always start from simple models, right? That's why I suggest you guys not to start with deep neural nets first. Try to start with linear models, right? And then try to make your model more and more complex, right? And if nothing is good for the simpler models, at least they form some baseline, which can, based upon that, you can further improve, right? You can compare with those simpler models to show that your new models are better, right? Another common knowledge is that if you can combine multiple models and algorithms together, it usually tends to work better. And finally, before you decide to use machine learning, right, think about whether your problem is learnable or whether it is worth a machine learning approach. Any question? Okay, thanks. And wish all of you great success in the future. And I really appreciate your efforts throughout the semester. This class is not easy class, but hopefully this class indeed can give you some sense and practical experience about machine learning. Okay. So yeah, that's it.
Well, thank you very much.
Thanks.
Thank you.
Thank you.
Thank you.